So without further ado, please help me out welcoming Professor Chandler Zell.
So, thank you very much. Thank you for inviting me up here. This is the, I don't know, fourth time I've been here. It's always been very enjoyable visiting Waterloo, and thanks to all of you for turning out on what turned out to be such a beautiful day. And so it's hard to compete with this weather. So I'm glad to see people showed up. So I'm going to talk tonight about quantum physics, which probably conjures up images of these sorts of nonfiction books that emphasize, have words like puzzle and enigma and tend to emphasize the weird parts of the theory. And I'll do a little of that, but it's not really going to be just that. The other thing with quantum physics that you probably think of is that it's an empowering tool for any number of technologies. Because we understand the quantum nature of light and matter, we can make lasers that are the basis for modern telecommunications. Because we understand the quantum nature of electrons, we can make computer chips that power all of our fun electronic devices. And we have the ability to now manipulate matter on the scale of single atoms, right, which makes the nano part of this building go. So this is also a big area of quantum physics, but also not what I'm talking about tonight. What I'm going to talk about tonight is a different angle on things, and is the way that quantum physics turns up in fiction, and how ideas from quantum physics have had a profound influence, both as elements of stories directly, and also sort of as more general influence on ways of thinking about the world. So what I want to do tonight is talk about a couple of approaches to quantum physics that have been particularly influential and inspiring for people who write fiction, and then talk a little bit about some of the stories that these things show up in. Now, in order to do this, I have to talk a little bit about quantum physics in general first. And there are lots of places that you can start with that. I'm going to start here with this fellow. This is Louis de Broglie. As you can tell from his expression of mildly amused disdain, he's French. And he, as a PhD student in 1923, he made a remarkable suggestion. He suggested that electrons, which everyone knew were particles, should have wave nature, that an electron should behave like a wave. He did this largely for reasons of mathematical symmetry, because it had already been shown that light waves, which everybody knew were waves, sometimes behave like particles. And he said, well, if light waves behave like particles, maybe particles should behave like waves too. That's an elegant mathematical argument. It also seems a little crazy. But he had more empirical reasons for believing this as well. If you take his idea of electrons having wave nature seriously, it provides an elegant explanation for why there are these special orbits in atoms that electrons sit in. And this was the basis of the extremely successful Bohr and Sommerfeld quantum theory explaining the states in atoms. So he had reasons for doing this, as crazy as this notion of electrons behaving like waves seems. Once you have this idea, this is also something that is manifestly testable, right? You can go out and you can look for situations where electrons behave like waves. And by 1930, scientists in both the US and the UK had done experiments where they saw unambiguous evidence of electrons behaving like waves. Nowadays, we have a really beautiful illustration of this from an experiment that sends electrons at a barrier with two slits cut in it and detects them on a screen on the far side of the slits one at a time. Right. And as the electrons arrive one at a time, they show up at a particular place at a particular instant, exactly like you expect for particles. But if you repeat this experiment over and over and over again, all of the electrons together trace out a pattern of bright and dark stripes. Right. This is a signature of wave behavior. All right, so how is that a signature of wave behavior? Well, we have to look at some actual waves, right? So here's waves in a thing that you expect to have waves. This is a puddle of water that a bumblebee has fallen into. I should tell you that the photographer who took this did note that after taking the photo, he scooped the bee out of the water. So it survived, and so I don't have to worry about that. This bee is in the water. It's flapping its wings trying to get out, and each wing is generating a pattern of waves. You can see them expanding out in concentric rings. Okay. But there's this area in the back where the waves from each wing overlap, where something really complicated and interesting is happening. Right. What's going on there is that the waves are adding together, and the result of adding those waves together depends on exactly how they arrive. Right. If both sets of waves arrive so that the peaks of one are on top of the peaks of the other, then you get a much bigger wave. Right, and that accounts for these stripes where you have these extremely prominent waves in the back. On the other hand, if one of the waves takes a little longer than the other to get there, right, then the peaks of the one fill in the valleys of the other, and you get nothing at all, which accounts for these rows of flat water. This is a characteristic behavior of waves. It's called interference. Right, and this is one of the things that proved to everyone that light is a wave. Right. And this is what's going on in this experiment with the electrons. Right. If we look at the electrons, we see these patterns of bright and dark stripes. We see places where there are lots of electrons. That's where the waves associated with the electrons arrive so that the peaks of one are on top of the peaks of the other. And we see these dark stripes where there are very few electrons, where the peaks of one wave are filling in the valleys of the other and leaving you with nothing. Right? So this experiment demonstrates that electrons behave like particles because each one is detected at a specific place at a specific time, just like a particle, but also behave like waves because there's this overall interference pattern that's characteristic of wave behavior. Richard Feynman, I'm contractually obligated to mention Feynman at some point in any public talk about physics. Richard Feynman famously said that this experiment, this double slit experiment with electrons, embodies the central mystery of quantum physics. Right? Everything weird about the theory sort of follows from this experiment. So it's a good place to start. So we have this idea that electrons behave like waves. Well, if electrons behave like waves, then there should be some math to govern this. There should be a wave equation. That was generated by this happy fellow here. This is Erwin Schrödinger, an Austrian physicist, who came up with the equation that describes the wave nature of material objects. That's the Schrödinger equation up there. It's mostly decorative. I'm not expecting you to calculate anything with it at the end of the evening. I just put it up there because it looks very nice. It's a very elegant, aesthetically pleasing equation. People sometimes get a little carried away with that, and I really don't know what that is there, but it's a nice equation. Right. What this equation gives you is a thing called a wave function. It's represented by this capital Greek letter psi that shows up in there. And that wave function is describing the properties of the electron that's in there. But now a question you can quite reasonably ask at this point is, what is that wave function doing? Right? It's not the electron itself, right? Because the electron itself gets detected like a particle at a particular point at a single instant in time. Right? So the waviness, a wave's a disturbance that extends over space, over some region of space. This wave function has that property, right? But somehow it's also connected to this particle-like electron. So this was a problem. This caused people some concern. But eventually, an interpretation of this was reached thanks to this guy. This is Max Born. German physicist, whose work is commemorated in this Google Doodle. And he spent a lot of effort working out what exactly is it that the wave function tells you, and he came to the conclusion that the wave function is connected to probability. Right? What it's telling you is something about the probability of finding the electron at a particular point at a particular time. Right? And that's what you see, really, in this experiment with the electrons. Right, what you're seeing is something probabilistic. Right? There are places where the probability of finding an electron is very high. Those are the bright stripes. There are places where the probability of finding the electron is very low. Those are the dark stripes. Right? But this doesn't tell you exactly where any individual electron is going to end up. The only way you can see this pattern is to repeat the experiment many, 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 many times, and then all of the electrons together trace out that pattern. This is a really important development, because it lets people start to interpret this wave equation of Schrodinger's, and this gets you lots of rapid progress in quantum physics. It's also kind of disturbing, because this is the thing that brings in the element of randomness, the rolling of dice that famously disturbed Albert Einstein about the nature of quantum physics. Right? You can't say where any particular electron is going to end up. All you can do is say what the probability of that electron landing at some place is. Right? And that's kind of disturbing to physicists who are trained classically. This is the issue here is you have these wave functions that are very nice, and you have an equation that governs them, and you can do calculations with them and all that sort of thing. And they predict very accurately the probability of finding an electron at a particular place. But they don't tell you why that one electron there ended up at that particular point. There's a middle step to this process that is shrouded in mystery. And that's the thing where a lot of effort goes into understanding what's really going on in quantum physics, or at least theorizing about what's really going on in quantum physics. The state of the actual electrons is a funny thing. The state of the electrons is indeterminate. They could be in many states at once, or in the case of the double slit experiment, they're simultaneously in the state of having gone through the left slit and having gone through the right slit. It's hard to illustrate this, but I think a really nice illustration I've seen used, I got this from Chris Monroe and Dave Wineland, is this cube that we teach small children how to draw when you're trying to draw in 3 dimensions. This thing is a figure that is 3-dimensional, but ambiguous. If you look at that cube, that could be a cube that's facing up and to the right, or it could be a cube that's facing down and to the left. And if you look at the figure without the shading, with a little effort, you can make yourself see either of them. You can look at it and sort of force your brain to see it as a cube that's up and to the right, or you can switch it to be a cube that's down and to the left. And if you do that long enough, you give yourself a blinding headache. This is sort of like the situation of these electrons. They're in these indeterminate states. They can be in multiple states at the same time. It's not determined what they actually are. But somehow when we get to the final experience of reality, something is shading in one face of this ambiguous cube and getting you something that's a definite result. And that's the step that's mysterious in this process. How you go from this probabilistic thing where the electron can be lots of places at the same time, and in some sense is in lots of places at the same time, to a situation where it's detected at a particular place at a particular instant in time. That's a really mysterious thing. That's something that people worked hard to try to understand. Well, actually, one of the first approaches to this was just to say, well, it doesn't matter, because this only applies to things that are microscopic, like electrons, and if you're talking about big things, then big things are governed by sort of common sense classical physics rules, and we don't have to worry about any of this weird quantum stuff. That doesn't really work, though, and the guy who's most responsible for showing that that's an untenable position is the guy who came up with the wave equation, Erwin Schrödinger. He got disillusioned with the whole business, and in 1935, he wrote a long article that was sort of his exit statement as he left quantum physics to go work on other problems, in which he introduced the most infamous thought experiment in the history of science. It's called Schrödinger's cat. And what he imagined is taking a cat and placing it in a box with a device that contingent on the decay of a radioactive isotope, would kill the cat. So if this radioactive isotope decays, then it smashes a vial of poison and the cat dies. If the isotope doesn't decay, then the vial stays intact and the cat stays alive. Now he said, you imagine sealing this up so you can't see the cat, you can't hear the cat, you can't smell the cat, you can't tell what's going on inside the box. And then you wait an hour, and after an hour, there's a 50% chance that atom has decayed and the cat's been killed. And he said, what's the state of the cat at the end of that hour? Now, common sense would tell you that there's a 50% chance that the cat's dead, and there's a 50% chance that the cat's alive, but it's definitely one or the other inside the box. But he pointed out that the state of that atom, the state of the atom, quantum mechanically, is this indeterminate 50-50 mixture of, right, it has decayed and not decayed at the same time. It's in this indeterminate state until something happens to measure it. And now this state of the cat is inextricably bound up with the state of the atom. Right? If the atom has decayed, then the cat's dead. If the atom is not decayed, then the cat's alive. But if the atom's in this 50-50 superposition of decayed and not decayed, then the cat should also be in a 50-50 superposition of alive and dead at the same time. That's an utterly bizarre kind of situation, right? But it's a logical consequence of the applying the principles of quantum physics, and also shows that you can't just hand wave this away. You can't just say this only applies to electrons, big things don't have this property. That you can tie together big things and little things in a way that creates problems and forces you to grapple with the fact that there are these indeterminate states that somehow become determinate when you measure them. So there are a number of approaches to trying to address how this problem gets resolved. And those approaches are the things that I really want to highlight that go into inspiring lots of fiction and literature that deals with quantum themes, or is just sort of inspired by quantum as a metaphor for other things. Right. And there's two main categories of approaches to this. The first of these gets named after the city of Copenhagen in Denmark. Copenhagen's a beautiful city, as you can tell from the photo. What matters here is not that it has water or brightly painted houses, but that it's home to the institute founded by Niels Bohr, who's one of the pioneers of quantum physics. And he was a big proponent of this particular interpretation of quantum physics. And what sort of the nickel summary of Copenhagenism is that you have these wave functions that give you a probability distribution that has lots of wiggles and bumps in it and so on. And this tells you how the indeterminate state of some particle is spread out. And then you introduce an observer, right, who comes and looks at that state and makes an observation. And as soon as that observer looks at the state and makes a measurement of it, that state changes. Right? You no longer have this spread out probability distribution. You collapse to a single definite value. All right? And it's that active observation that causes a real change in the system that you're dealing with to go from this indeterminate state to a definite value. In that picture of the indeterminate cube, this is the thing that shades in one face of the cube. Right? Somebody coming and looking at the system to make a measurement of it. This is an idea that's had a big influence on fiction, and it shows up lots of places. One of my favorite statements of this comes from a short fiction contest that is run by a number of institutions, including the IQC as one of the sponsors of this contest, called Quantum Shorts. And this was from 2015, a story called The Qubits of College Acceptance from Lily Tarosky. And this is a story about a young woman who has the same name as the author of the story, who has a collection of envelopes that she's received from various colleges sitting unopened on her kitchen table. And the reason they're sitting unopened is because she finds this empowering. Right? There's comfort in knowing that she has the power to change the course of her life, because it's not the envelopes that control her fate. It's her decision to open the envelopes that determines whether she got in or didn't get in. So as long as those envelopes are unopened, she has been accepted by all 8 Ivy League universities. She's also been rejected by all 8 Ivy League universities, but you can focus on the part where she's been accepted by all 8 Ivy League institutions. And it's this idea of that it's the measurement that creates the reality, that takes you from this indeterminate state of being both accepted and not accepted to a definite reality. This is a very short story. I won't spoil the punchline, but you can go and look it up on the web and read it there. And it's quite well done. This notion of observers creating reality is absolutely central to the Copenhagen picture of how quantum physics works. And this is described by, you find lots of statements from the pioneers of the theory. This is Werner Heisenberg saying that on a philosophical level, what science is describing is not objective reality, but nature as exposed to our nature of questioning. Right? That what you learn about nature depends on what questions you ask and how you ask them. And Niels Bohr, whose institute gives the interpretation its name, has this much wordier statement saying that it's no longer possible to make predictions without reference to the observer or the means of observation. Right? Saying that the nature of reality is inextricably bound up with how do you measure the nature of reality. Right? And in some sense, you're creating the reality that you see through the experiments that you do. Probably the strongest statement of this comes from, this is John Wheeler, who was at Princeton, an enormously deep and influential thinker about these things. And he had this sort of very poetic picture, this history of the universe, that he has the universe sort of starting from nothing and evolving and expanding and getting more complex until such time as it is capable of supporting creatures that are complex enough to, as the eyeball, look back at the history of the universe and collapse that to a single reality that gives you a coherent history of the universe leading up to the creation of those beings that are observing it. So it's the universe observing itself into existence. Which is, a really interesting idea. Right, Wheeler was big on this. This seems superficially extremely flattering, as the beings who are building telescopes and looking out into the universe and, tracing history back to the Big Bang and creating all this. It seems kind of flattering. This is not necessarily a good thing. There's a novel by Greg Egan, an Australian writer. This is about 20 years old now, so I'm going to spoil the ending because it's 20 years old. This book called Quarantine, which starts with the stars going out. Starts with the Earth being shrouded in an impenetrable darkness that doesn't let you see out into the outside universe. And it eventually emerges that this has been done by aliens who would really rather that we didn't observe the history of the universe and collapse everything into a single history that leading up to us. Right? And so it's a really interesting twist on Wheeler's sort of approach to the universe. And this is kind of Copenhagenism taken to an extreme, where it's suggesting that humans have a sort of a special ability to do this observation and collapse these wave functions in this way. Now this is also, these are ideas that have a powerful influence not just on genre science fiction like Egan is writing or the quantum short stories. These also show up in much more literary contexts. This is on the left here, we have a book of literary criticism by Samuel Chase Cole, talking about the influence of quantum physics on a lot of postmodern ideas. And this notion of observers creating reality is something that fits very well with a postmodern approach to literature. Right? The idea that the world is what you create for yourself by the process of observing it is something that's extremely powerful in that context. And he points out that this fits very well with any number of books. I'm picking just a couple of them here. Pynchon's Crying of Lot 49. This is a book where characters are wandering around and uncovering what may be a centuries-old, extremely powerful conspiracy, or it may just be something that's kind of being made up as they go along. And it's never quite clear what the reality is. Right? That's a thing that fits very nicely with this idea of observers creating reality, right? And it's a sort of fluid and it's a world that doesn't necessarily make an enormous amount of sense. This also highlights DeLillo's Underworld, which is a fantastic book. I'd highly recommend. Just the prologue of it is amazing. Story about the baseball game. this is a sweeping sort of history of America, but it's tied very strongly to the perspective of particular people and how they observe those events. And so that also fits in very well with this idea of observers creating reality as they experience it. I'd also say that another category of stories that are influenced by this, though not directly, they tend not to directly reference quantum in any way. Cole points out, by the way, that DeLillo, while writing this, has extensive notes in his diaries and notebooks where he's reading a ton about quantum physics and the Copenhagen interpretation and obsessing over these things, and that's a powerful influence on his work. An area where there's less of a direct influence, but you can see some sort of commonality is the genre of stories where people find out they're a character in somebody else's story. There's a Will Ferrell movie, of all people. He's not actually manic in this. It's a really interesting movie where he finds out that he's a character in a story being written by Emma Thompson, who is a famous novelist, and then has to come to terms with that. And something that actually is manic but doesn't feature Will Ferrell is John Scalzi's Red Shirts, which is, the title comes from the red uniforms worn by the extras in Star Trek TV shows who beam down with the bridge crew to the planet and then instantly die because they're not really important to the show and you need to do that. It's a story about a ship sort of like the Enterprise, in which a bunch of these people realize that they are characters in a badly written TV drama and decide to do something to solve their problem, right, to avoid having themselves killed. So it's a fun book. So those are that's a quick version of the Copenhagen interpretation of quantum physics and some stories that thematically fit in with that. I also want to mention the other really big interpretation or category of interpretations in some sense. There are, each of these interpretations that I mentioned has about as many versions as there are people who have thought seriously about these interpretations. Everybody's got their own little twist on it. The other one of these, to explain it, we need to go back to Schrodinger's infamous cat in a box experiment. Think about this cat that's alive and dead at the same time. And the big problem that this poses is how do you determine whether the cat ends up alive or dead when you open the box? Right? What is it that determines which thing you see? What is it that makes the superposition that quantum physics says should be there collapse into the single reality that we observe? Right. The Copenhagen approach is to say that the act of opening the box and observing the cat causes a real change that picks out one possibility or the other. But the alternate approach, one of the biggest alternate approaches, is to say that you don't need that at all. Right? You can continue to have both, just in separate universes. And this is what's known as the many worlds interpretation. This is nice illustration of this with a sort of a film strip, that at the instant that you observe the state of the cat, the world sort of bifurcates. It splits into a universe where the cat is alive and a universe where the cat is dead. Right. This was pointed out by, on the left here, Hugh Everett III, who was a graduate student at Princeton, his PhD thesis. Came up with this idea, and he points out that if you just do that, you don't need to change anything about physics, right? The problem that people have with the Copenhagen interpretation is we have this Schrodinger equation, it works very nicely, and then something sort of magical happens when you make an observation, and then you go back to using the Schrodinger equation again to describe how things work. There's this magical step that nobody knows how to describe, right? Whatever it says is if you just dispense with the need for that magical step, then you can just continue to have everything in multiple states all the time, and you can continue to use the Schrodinger equation all the time, and nothing weird needs to be done to physics. How does this work? The way to see it is to imagine this scenario with Schrodinger's cat in a box. So you got the cat in the box with something that's a 50% chance of killing it. All right, and then you also have Schrodinger, who set up the experiment, and his friend Einstein, who is anxiously awaiting the results of the experiment. And mathematically, you start out with a universe in which each of these things is in one definite state. Right? You have one Einstein, you have one Schrodinger, you have one box with a cat and all the other crap in it. All right. And mathematically, what happens is, the atom either decays or doesn't, at which point your box then sort of splits into, now I've got a cat that's alive, and I've got a cat that's dead. All right? But none of the other two know what's inside the box yet, so they remain in single states. All right, the cat in the box is in this both states at once situation. All right. When Schrodinger opens the box, right, in the many worlds interpretation, all that happens is he goes into a superposition as well. Right? He's in a superposition of having opened the box and found a live cat and having opened the box and found a dead cat. Right? He's in both states at the same time, but those states are tied together, right, entangled with the state of the cat. Right? There's a piece of the wave function that has the dead cat and also has the Schrodinger who found the dead cat. Right? And there's a piece of the wave function that has the live cat and also has the Schrodinger who found the live cat. Right? And Einstein, who still doesn't know the result of this, he's still in just a single state. Right? It's only later when Schrodinger tells him the results of the experiment that Einstein, too, joins in this giant superposition. And you have an Einstein who knows that the cat was alive and an Einstein who's just learned that the cat was dead. Right? And this process continues. You can bring in other people, right? The reviewers for the journal article about the live and dead cat, the copy editors, right? As different people find out, they all join in this ever-expanding superposition of being in two states at once that are related to the knowledge that the cat is either alive or dead. Right? What you have is this giant expanding wave function. It has lots of pieces where everything is, but all of those pieces are just individual people and observers and entities that are all in multiple states at the same time. Right? But those states are correlated with each other in such a way that you get a completely consistent and coherent history for each of these branches. And these branches are totally separate from each other. Right? They behave as if they were separate universes. Right? Once you're in the branch where Schrodinger has learned that the cat is alive, right, everybody else is going to also learn that the cat is alive, and they just get correlated with that and continue along. Right. Well, so how is that, or why do we not see things, why are these things completely separate, right? Why do we not see the existence of these other universes? We don't see the existence of these other universes for reasons that are, again, contained in this experiment involving electrons going through slits, right? These electrons going through slits, the only way that we know that the electron is behaving like a wave is by repeating this experiment many, 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 many times. Right? We can trace out this probability distribution that shows that the electrons went through both slits at the same time only by doing the experiment over and over and collecting all of the results to determine the probability distribution. A single realization of the experiment just gets you one dot on the screen saying that the electron was detected at this point at this instant. Right? It doesn't tell you anything about the probability distribution. To learn about the probability distribution, which is what tells you that the electron has wave nature and that the electron was in multiple states at once, right? To get that information, you need to repeat the experiment a lot. And if you're dealing with something like electrons, it's easy to repeat these experiments lots and lots of times and control the experiment well enough to be able to get consistent results. But if you're talking about something big, that's simply impossible. So what do I mean by simply impossible? I'll give you an illustration that we'll leave the cats in the boxes. My shtick is dogs. So I'm going to imagine here's a screenshot from Google Maps showing where we are tonight in the Quantum Nano Center. And I'm going to imagine doing a two-path sort of experiment, a two-state experiment with my dog. This is Charlie the pupper. I'm going to imagine taking him for a walk around the little rock garden that's right outside the building here. And we can go either clockwise around the rock garden or counterclockwise around the rock garden. And you can imagine this is a two-path sort of experiment where there would be some me and the dog wave that goes one way and a me and the dog wave that goes the other way. And how those are going to add together on the far side, to get you information about those paths is going to depend on how long it takes to go around there. Right? Well, that rock garden is pretty small. It's nice. It's well laid out. There's informative signage. But it's not very big, right? So that's a thing that you can control reasonably well. Right? If I go and I do this experiment where, on the flip of a coin, I go either left or right and thus, go both ways in a quantum universe, I'm going to get sort of consistent results as I go around. Right? But if I try to scale this up, I try to scale this up to going not around a little rock garden, but going around Waterloo Park, all right? I do the same thing. I can go around clockwise or I can go around counterclockwise, but this is going to be almost impossible to get consistent results out of, right? Because the clockwise path, I got to go by, I'm going to pass other dogs, and I got to go by the edge of the lake, and there's going to be birds, and there's squirrels, and there's stuff to sniff, and there's things to smell. The dog's going to stop and be distracted constantly. Right? If I go the other way, there's like a skate park, right, with humans on wheels doing tricks, and that's incredibly distracting. And maybe somebody's dropped some fries on the ground, and we got to stop and deal with that. There are all these uncontrollable environmental interactions that scaling this up introduces. Right? If I try to do this experiment over and over, I'm not going to get consistent results because there's all of this other stuff from the rest of the universe coming in that's keeping me from doing the experiment the same way every time. Right? If I'm dealing with a small path, I'm dealing with something like the rock garden, I can control that stuff. Everything's going to be pretty much the same for both paths that the dog would take. Here, it gets big, right? It's not going to be the same experiment every time. And if it's not the same experiment every time, I'm not getting the same probability distribution every time. I'm going to get something that looks like nonsense. I'm not going to see that the dog and I went both ways in the wave function. That we're in a superposition of having gone each direction at the same time. Right? This is essentially what separates the different universes in the many worlds interpretation. If you're dealing with things that are small, right, you can see quantum effects because you can control those things well enough to be able to do the experiments repeatably every time. Right? If you look at work that's going on here at the University of Waterloo, right, there are these wonderful experiments with nanoscale spin systems looking at quantum effects and phenomena in those. But these things are tiny. Right, that picture on the lower left there, that whole square is about 1/10 the diameter of a human hair. Right? These are extremely tiny systems that are extremely carefully controlled in order to be able to see that kind of quantum effect. Right? And other experiments that go on are sort of extravagantly shielded. There's this really nice photo of the group responsible for these NMR experiments posing in front of their apparatus, which is this big blue tank that's behind them. And that tank is there to shield the experiment from every outside influence. Right? It's cooled down to a few degrees above absolute zero. There's magnetic shields and all sorts of things to protect the quantum system from the influence of the outside environment. If you're dealing with small things and put in enough effort, you can see these effects because you can do the experiment the same way every time. Right? On the other hand, by the time you're talking about something the size of a cat, right, that there's just so much stuff for it to interact with. There's so many atoms in a cat. There's so many atoms in the walls of the box and all the other stuff that are going to be a little bit different every time. That means that there's no way for you to do the experiment the same way and get consistent results. And that's going to lead to you not being able to tell that both of these universes exist. Right? In fact, every time you do this experiment, right, there is a probability ultimately of what the outcome of your experiment would be that is completely determined by the fact that that you need to account for both branches of this to determine what exactly that probability is. But since you only get to do the experiment once under those exact conditions, you can never determine what that probability distribution is, and that's what you would need to do to see that both of those branches are there. So this gets you this separation of the world into multiple universes. However, you're never really going to see the presence of these other things involving macroscopic scale objects. At least not in the real world. That doesn't restrain people who write fiction. This many worlds interpretation has been an extremely rich source of inspiration for lots of writers over the years. Probably the absolute best, I would say that this story is the best fiction I have ever seen about quantum mechanics ever in anything. This is by Robert Charles Wilson, American-Canadian writer. It's called Divided by Infinity. It was originally published in this collection called Starlight 2, but it's been reprinted by Tor.com. So if you search Divided by Infinity, you can find this story. It's awesome. Highly recommend it. And in this story, there's a man who has some weird experiences, then he's given a book that explains a version of the many worlds interpretation and puts a really interesting twist on it. Right, he says, there's a description of, at birth you begin to experience lots of different universes, and you divide into, 2, then 4, then 8, right? And the universe expands exponentially the different versions of yourself that exist out there. But there's this element of observation, of consciousness that's connected to all of this, right? That the key to defining these branches is that you're part of the wave function that's experiencing this universe. But he points out in this that the upshot of this is you cannot die. Right? And what do they mean by that? They mean by that by definition, you can't experience your own death, right? Because death is the cessation of experiencing anything. Okay? And therefore, right, if you continue to experience the universe, this ever-expanding wave function, right, your experience of it is limited to those pieces of that ever-expanding wave function in which you are alive to experience it. Right? Therefore, right, you always wake up every morning not dead. Right? You will never die, according to this twist on the many worlds interpretation. Which makes for a fantastic story, and I highly recommend reading this. It would also be, if Wilson hadn't written this story, it would also be a great way to make money from really gullible people if I had no ethics whatsoever. But it is one of the best statements of this version of quantum physics that I've ever seen. And the key thing is that this seems ridiculous, right? It seems improbable. But as he notes, right, you don't die, you just become increasingly unlikely, right? No matter what situation you're in, as long as there is some outcome where you continue to be alive, that's the one you're going to experience, all right? And this is a key element of the many worlds interpretation. This is the thing that causes a lot of people to part company with many worlds proponents, is that this tells you absolutely that there exist out there universes in which things that are highly unlikely but possible happen. All right, so anything that has a chance to happen happens somewhere out there in the universe. So, this is still a possibility, okay? It could be true that, as Larry Fishburne is telling you, that the Raptors will win the NBA championship. That's still a possibility. And since that's a possible outcome, you know that somewhere out there in this ever-expanding, exponentially growing wave function of the universe, there is a branch where that happened, or that will happen, right? You can say with certainty that will happen somewhere. And this applies even to things that are outlandishly unlikely, such as this is an image from a parallel universe in which the Ottawa Senators won the Stanley Cup. Okay, it's not really, it's from a video game, but which tells you something about fandom, that you can go and if you search Ottawa Senators Stanley Cup, you find numerous versions of this picture where somebody played a video game as the Senators won the Stanley Cup and then screenshotted this image. But this is true, right? In many worlds, no matter how ridiculously unlikely a thing is, it's happened somewhere out there in the multiverse. This is an idea, again, that has extremely obvious fictional possibilities and gets used lots of places and lots of ways. Here's a few books that invoke this in one way or another. On the left, this novel by Paul Melko has a character actually careening through lots of different alternate universes in which the history of things has gone differently. And that's a really good one. There's Neal Stephenson, or it's a great big thick book because it's by Neal Stephenson. He only writes great big thick books. And it's a whole grand intellectual history of an alternate universe that ends up bringing in these ideas. And this is the most recent of them, Joe Walton's book. It involves an elderly woman who has memories of 2 different realities. And is experiencing both of them, or remembers having experienced both of these realities, which is a fascinating way to look at this. This also shows up not just in books, but also on screen. The TV show Fringe that ran for quite a few seasons involved characters going back and forth between our universe and an alternate one. And of course, there's the Amazon series Man in the High Castle, which is actually based on a Philip K. Dick novel set entirely in an alternate universe in which the Nazis won World War II. However, it becomes clear in the book, I don't know what will happen in the TV show, it becomes clear in the book that they are in fact in one of these extremely unlikely alternate universes, that their reality is actually kind of thin. And so it's both an alternate history story and a what if sort of sense, and it's also a little postmodern because Philip K. Dick was a weird dude. So. And I'll also call out a story from the Quantum Shorts this year, and this is called Acceptable Loss by, I'm not going to attempt to pronounce that name. But this is one of the winners this year in the open category. And this concerns a scientist talking to someone who's having a reaction to this that many people have on hearing this is, well, like, what do we have to do to put an end to this multiverse nonsense, right? And he's talking to a military man and saying, like, we have this device that can destroy all of the other universes. And, that's kind of a big deal, right? So the general in this story is a little hesitant to push the button on the device that's going to destroy all of the alternate universes and get back to just a single universe. However, as the character points out, right, there's a problem where, if you have all these alternate universes, there is some other universe in which somebody else had the idea of how to make the device that destroys all of the other universes. And if you don't push the button in your universe, then one of them is bound to push it in theirs. And this is another idea that's had a lot of influence on people. People have spent a lot of time thinking about this, and it's sort of interesting to think about, like, what is the impact on ethics of knowing that in this universe, right, no matter what you do, right, there's also a branch of the wave function out there somewhere where you did the opposite, right? And so that's a problem that comes up that people talk about a lot. And I don't know that there's a good resolution to it. This story has a good resolution. You should go check it out because it's well done. So that's my attempt at a gloss of quantum physics, interpretation of quantum physics, and how that's had influence on literature, right? And stories that have been inspired by that and influenced by these ideas. And really, the key to this is both of these interpretations give a really critical role to the experience of the observer, the person who's observing the world. In the Copenhagen picture, right, it's that the reality is being created by the person who's doing the observation. The observer stands somewhat outside the wave function, and their action on it causes a single reality to emerge, right? In the many worlds, right, the observer also has a critical role, but here they're pulled into the wave function, right? In the process of observing what's happened, the observer becomes drawn in, becomes entangled with these multiple realities that continue to exist. These are the two biggest approaches to quantum physics. And they each come in lots of flavors. And this has inspired lots and lots of writers of various genres and fields and approaches. The books that I mentioned really only scratch the surface. Here's a collection of other things that have ties to these interpretations of quantum physics. There's some alternate history books here. There's some books with multiple realities. There's some more postmodern sort of things where the emphasis is on the fluid nature of reality and it being created by people's experience of it. I recommend all of these. And The Arrival is a movie. I'll mention that the short story on which it's based is even better than the movie, which was really good. So you should look that up. It's called Story of Your Life by Ted Chiang. That is what I wanted to say about quantum physics and literature. I hope that's been interesting, and I'd be happy to answer any questions that you have.
Thank you very much. Anyone would like to ask questions?
Can you go back to explaining your analogy with the dog, the garden versus the park, and just tie that to what you were talking about, small systems like electrons versus large systems like cats? Because that was a lot to take in.
Yeah, that's a little heavy. So the idea is, right, if you have a small system, right, if you want to know that there are multiple universes, that there are multiple components of the wave function that are interacting, the way you do that is you have to do some sort of interference experiment. You have to let the universe separate into two pieces and then bring them back together, right? And after you bring them back together, you'll see an influence on the probabilities from that. But if you want to measure probabilities, you have to do that separation and recombining exactly the same way every time, right? Otherwise, you're going to get nonsense. Otherwise, your probabilities are going to be skewed by the fact that the conditions of your experiment were not the same. So if you're talking about, the point of the dog analogy is if you walk on a short path, right, it's going to take you about the same amount of time to walk around that rock garden every time, right? Because it's a very controlled, it's a small controlled area. And even if a squirrel shows up in the middle of the rock garden, right, it's going to affect both dogs equally. Right, because both of them are going in opposite directions. They're both going to see the same perturbation, the squirrel that shows up, and they're both going to react in similar ways. So your results will be fairly consistent, right? If you go to something much bigger, right, you go to the much bigger pack, those dogs are out of sight of each other, right, all the time, and they're experiencing completely different perturbations. Right, one dog is seeing a squirrel, the other is seeing a kid on a skateboard. They're going to react differently, and every time you do it, they're going to see different sets of different perturbations, right? So the dog, the first time they saw the squirrel, is going to not see anything. And the one that was distracted by kids on skateboards is instead going to meet another dog, and they're going to play fight for a while. And the conditions of those experiments are completely different every time. So the results won't be consistent, right? Which dog arrives first, right, by how much is going to be totally random every time because there are all these external factors that are changing the conditions of the experiment. Now, if you carry this over to thinking about physical systems, you're talking about single electrons inside an ultra-high vacuum system that are just, they interact with two slits and a screen. That's a really simple system that you can control everything and get consistent results out of. Right? You want to do the same thing with squirrels or cats or dogs, right? They're really big. Right, a dog has 10 to the 20-something atoms in, right? So it's it's a billion, it's 1,000 billion atoms. Each of those is interacting with all of the other atoms of all of the air in the room and the walls of the apparatus and all these other things. You just can't control it to the level that you can a small system. And that means that every time, if you try to do these quantum sorts of things with big systems, right, it gets harder and harder to do those experiments. Now, there are people who've made a really nice career out of. There's a guy named Marcus Arndt, who's in Austria, who his whole career in physics is sort of doing multiple slit interference experiments with bigger and bigger things. And they've worked their way from, single atoms up to, carbon-60 molecules, those buckyballs, up to these like big floppy organic molecules that have these long side chains and hundreds of atoms in them, with a goal of trying to get up to, things that are like viruses and blood cells and that scale. But it gets harder and harder to do the experiment because it's harder and harder to control the conditions to the level that you need to be able to do that repeatedly and get the probability that you want to measure.
So it's a good analogy for defining.
I've been wondering, the people that formulated the formulas that we go by now were only working with about 4% of the universe, the visible light. Now we've discovered dark matter and dark energy. I was wondering if that has had any impact on any major equations or anything like that.
I mean, the influence of dark matter and dark energy show up on sort of on grand scales, right? We can see that they're there by the gravitational effect on, galaxies, so sort of that scale. Or, for dark energy, we see the increasing rate of expansion of the universe as a whole. It hasn't penetrated down to the level of things like the Schrodinger equation, though really the Schrodinger equation is more of a high-level description than you would have with these, just because we don't know yet what the dark matter is. There are lots of theories of, that it's this kind of particle or that kind of particle or this kind of particle. So far, nobody has found any of the kinds of particles it was theorized to be. If somebody goes and somebody eventually finds one of these particles and say, okay, the dark matter is this thing specifically, then the different properties of that will change some equations and lead to different formulations of the equations of physics. But since we don't know yet which of the many things it is, there's no definite change to anything. In fact, the biggest problem that, in some sense, the biggest problem that really fundamental physics faces is that the standard model of physics is too good, right? Like everything keeps working too well. The stuff that we know now they keep testing at higher and higher precision, and it keeps working just fine, and everybody's rooting for it to break, and it just hasn't yet. So.
Anyone else?
I just had a question. I'm getting back to sort of earlier on in the talk. I'm just a little unclear on what's the hypothesis for why observation is special. So like if we get back to like the Schrodinger's cat concept, if we're thinking like why is the observation necessary to split the universes or to collapse the wavelength function? What if, like for example, instead of the decaying atom poisoning the cat or not, it was setting off a bomb that destroys the world or not?
Right.
Would that bomb not go off then until we opened the box? Or like, I mean, like that's where I'm confused. Is how where's the causation come into play there?
And that is, to a large extent, that is the primary objection. That's why there are interpretations other than the Copenhagen, which is, how do you get that? Like, what is it about observation? What counts as an observation, right? Can the cat observe things, right? Cats, they're not as smart as dogs, but they're intelligent-ish, and so could the cat be an observer? And you get into all sorts of questions about that. There are ways to handle these kind of situations in a Copenhagen-ish context where you can use the same argument about environmental interactions and stuff, the decoherence that I was talking about in the many worlds context. You can use that to sort the possibilities for the cat into definitely alive or definitely dead, and have it be definitely one or the other before you open the box. But there's still no way to pick out which of them it's going to be at the instant you open the box. And the reason that people put such prime importance on this is, well, nobody actually kills cats in boxes, but you do an experiment that has two possible outcomes. You only see one of them, right? You flip a coin, you see either heads or tails, or if you're incredibly lucky, maybe it comes and lands on its edge. But that's it, right? You don't see heads and tails at the same time. And so just trying to explain that fact, given the math that says it should be both of them at once, is the reason why that stuff has to come in. And observation plays a role in both of these pictures, right? Because you've got, even in the many worlds picture, it's what's distinguishing one universe from the other is the experience of the people who are in it. Right, or they're the ones who are seeing a single reality, not even though they're seeing that while existing in multiple states at the same time.
Okay, we have time for one last question.
So I was wondering if this is just a follow-up to the previous question. So you didn't really mention, for example, Bohmian mechanics or something. There's not enough literature on that, or because there you would have a relatively observation would not be fundamental in that sense, right? Like there would be an account of how measurement outcomes arise.
I think so Bohmian mechanics, if you're not familiar, is another way of looking at this by David Bohm, who realized there's a way to formulate quantum mechanics where the electron is always in a definite state. It's always at a definite place, a definite time, but it's guided along its path by some other quantum field that influences it. That is still, though, consistent with kind of the Bohr-Heisenberg approach to things, because the contours of that field that's guiding the electron are determined by, what have you set up your experiment to measure, right? You've set up your apparatus in such a way that it's going to measure this thing. That determines the quantum potential through which that electron follows a definite path. And so the act of observation still plays a key role in, not in the same collapse of wave function kind of way, but it's setting up the conditions in which things, in which the electron operates. And there's still some spooky stuff happening there. It still has to be non-local. It's the other big thing, but I'm not going to go into Bell's theorem. But yeah, Bohmian is a very interesting approach, and there's some cool stuff done with it. But it's niche enough that it hasn't really led to a lot of fictional treatments. So.
Let's thank again Professor Orzel, and have a good night.
Thank you.